Hi everyone. I wanted to record a quick video to sum up our discussion of the limit and to look at some quick consequences of our limit definition for scalar and vector fields. So just as a reminder, right, we have this definition of the limit of a function from some set S, which is a subset of Rn, into Rm. And we've observed that this limit definition, it really is essentially the same as our definition for the limit of a function from some subset of R into R. Really, the only real difference here is that I've replaced absolute values here with a norm, this being the norm on Rm, and replaced absolute values here with a norm, in this case, the norm on Rn. So again, this is the norm on the range space. This is the norm on the domain space. But fundamentally otherwise, the definition really is unchanged. We've seen algebraically that can make things a little bit trickier if you're dealing with a norm and you have several components potentially. It could be algebraically more difficult to work with. But fundamentally, the definition of the limit isn't very different. We're just swapping out absolute values for norms. Now, the other thing we have observed, however, is that because we are now looking at functions from Rn to Rm, there are a lot of different ways, right, we can approach the value a. So we looked in the previous video at limits along paths, right? When we're just in R, there are fundamentally only two ways to approach a fixed value a, from the left and from the right. However, when we look at functions whose domain is Rn, right, and we're looking at some fixed point a in Rn, there are many paths, uncountably infinitely many, in fact, paths along which you could approach a fixed value. And so while the definition hasn't changed much, the behavior of functions with domains of higher dimension, right, can be much more varied than a function that's just defined on R. So where we see some of that sort of more exotic kinds of non-existence of limits, it's not so much coming from a change in the definition, it's coming from just a change in the domain space itself, which allows different behaviors of the function that simply would not be possible if our domain was only one-dimensional. Now, what I want to focus this video on, it will be a relatively short video moving forward, is just some things that follow from this limit definition that are really in a lot of ways identical to what we saw in Math 5610 for functions from R to R. Right? So in particular, you get a very nice algebra of limits. So if you have two functions f and g, which both map from some common subset of Rn into Rm, and if the limit as x approaches a of f of x exists and is equal to some value, say L, and if the limit as x approaches a of g of x exists and is equal to, say, some fixed value m, then you have the following properties. So this first one, right, essentially says we can break up a limit over a sum. The second says we can pull out any scalar values, right? So if I have the limit of c times f of x, I can pull that c out, and it's c times the limit as x approaches a of f of x, which is just L. If you combine these two, you immediately get that you can break up limits over subtraction, because you could just rewrite that as plus a negative. Now, where this can get a little bit different, right? Normally, if we think back to 5610, we also showed things like being able to break up a limit over a product of two functions. Well, here, right, my outputs of my function are in Rm. They're vectors in Rm. So what is a product of vectors, right? Well, a product of vectors, one type of product of vectors, right, is the inner product. We're often thinking about the dot product. And it turns out here that we can also say that the limit as x approaches a of f of x inner product with g of x is equal to the inner product of L and M, right? So it's essentially the inner product of the limit of f of x with the limit of g of x. And then finally, and this almost follows directly from 3, because you can think of the norm of f of x as the square root of the inner product of f of x with itself. We also get that the limit as x approaches a of f of x sorry, we get the limit as x approaches a of the norm of f of x is equal to the norm of L. So essentially, I can push limits inside of norms. Now, again, these all work, well and nice. Certainly in our for functions from Rn to Rm. And you can prove each of these using the limit definition if you like. We're not going to bother going through that exercise in a lot of ways. A lot of the proofs are very similar to what we saw for functions from R to R. We simply need to take some care because we have vector valued things. Now we need to take care to replace some absolute values with norms, things like that, just to get the proof to work out. But fundamentally, the ideas are the same. So I just wanted to point out that we do get exactly the same sort of algebra of limits for vector valued functions and scalar valued functions of multiple variables as we did for functions of a single variable. The other thing, right, we normally think about, we define the limit, and then we want to use that to define continuity. And so we could do exactly the same thing. So if we want to define what it means for a function to be continuous at a point, we could write out this limit definition. We say f is continuous at a point A in the domain S if for every epsilon there exists a delta such that, so we have we have norm of f of x minus f of a is less than epsilon whenever x is in the domain and the norm of x minus a is less than delta. So again, that looks just like our epsilon delta definition of continuity from 5610 for functions from R to R. Again, we've just replaced absolute values with the appropriate norms. And again, you'll note that if A is an accumulation point of S, then the limit is defined, and essentially we can just say this is exactly the same as saying the limit as x approaches a of f of x is equal to f of a, which is exactly what we had before. Now again, when we look at specific examples, okay, it's still possible, right? These limits, because functions can have a lot more exotic behavior when they have more dimensions in the domain, there still may be, strange things happening here in this limit. Again, it's not because the definition of the limit is fundamentally different. It's simply because the behavior of functions that have domains of higher dimension can just be a little more exotic than they can on a simple one-dimensional domain. Okay, but again, sort of conceptually, there is nothing different between this definition and the definition we saw for a function from R to R. It really is the same idea that a function should be continuous when the limit as x approaches a is equal to the function value at a. Okay, so we're actually not going to say much more about continuity. We could spend some time, for example, discussing something like an extreme value theorem. So you can actually write down an extreme value theorem for functions from Rn to R. Okay, so we can't do one for functions from Rn to Rm because there's no way to order the outputs in Rm, or at least not a nice ordering. So there's no nice ordering of the outputs in Rm, but if they're in R, we can certainly order and say which one is the greatest. So we have a function from Rn to R, and we look at some compact subset of the domain, then the function must achieve its maximum value and its minimum value on that domain. Okay, so even with higher dimensional domains, we still get an extreme value theorem. Again, a lot of those proofs are almost identical, right? So we could look at our proof from 5610. If we just take things and modify them ever so slightly, we'll actually come up with the proof for a function from Rn to Rm. Now, again, we're not going to make that the focus of this course. In a lot of ways, as we mentioned in 5610, the study of those types of theorems is in some ways more about the topology of the space than any analytic properties of the space, even though it's a very useful result for doing analysis. So we're not going to emphasize those, but I did want to mention it briefly. Now, the one final thing I'll mention right? And this is again analogous to what we do for functions from R to R, right? We say that a function is continuous on a set S if it's continuous at every point of S. So in 5610, we might have talked about a function being continuous on an interval if it was continuous at every point in that interval, or it didn't have to be an interval, any type of subset of R, right? We could talk about it being continuous if on that set if it was continuous at every point. Same thing here. Again, the only difference now is this set S is a subset of Rn, right? So it's potentially some sort of higher dimensional subset that we could be looking at. So all of these things, once we have our sort of modified definition of a limit, right? A lot of these things, at least up to through continuity, work in an almost identical manner, at least conceptually, to how they worked for a function from R to R. Now, what we're going to see moving forward is that that is not true for everything. And so we want to spend our time really focusing in the next step on the derivative and trying to make sense of what a derivative and what differentiability ought to mean for scalar and vector fields. So this has been just a quick synopsis of all these things that are really the same, so that moving forward, we can spend our time focusing on what is going to be new and different in the context of scalar and vector fields.